I'm Steve Levides, and I'm a software engineer at Pixar Animation Studios, and I want to talk a bit about Hydra 2, which we've been working on for a few years, but we're starting to see an uptick of interest and use. So I've titled this like what can happen after scene description, and I'm going to go through the basic concepts and motivation for Hydra 2, some example usage of it, and then I'm going to hand it over to Dirk, who's going to show how they're starting to make use of it in experiments within Omniverse. So Hydra's origins is that it is an application-independent viewport renderer. In its first form, it was a scene abstraction API as a front end to a single OpenGL-based renderer, and that renderer was called Hydra. It is now called Storm for reasons that I'll get to. The idea of the scene abstraction API is that this viewport renderer can have multiple heads. So there's our like mythological analogy that we'll work with. So it was motivated by USD, but separable from it. So at the time, different Pixar applications had different viewport rendering systems, and when USD was born, there was an interest in saying like, okay, well maybe we can share one renderer, interactive renderer between all of these guys. So USD is just one of the heads of this Hydra. Later, this was extended to include a renderer abstraction API. And it's at that point where our Hydra metaphor is a little bit strained and we are less mythologically accurate because now we have multiple tails too. So the original design goals of this Hydra are still applicable, and I'm going to go over them. So it was supposed to be a lightweight interface. It wasn't supposed to get in the way. So it had minimal persistent state, and this notion of a scene delegate, you would implement virtual methods for these fixed fields like get mesh topology, get transform, get primvar descriptors and everything. And so the vocabulary that was expressed was specific to this one OpenGL renderer. There was an emphasis on lazy access because you don't want to read any data from the scene that you don't need. Because if we're storing a lot of information in USD, only some of it is going to be applicable to the interactive viewport. And the other primary goal of this was to make an API that enabled and sort of encouraged multi-threaded synchronization, because this Hydra renderer, now called Storm, was really good at consuming information on multiple threads. And so we wanted to make sure that the scene abstraction API did not get in the way of that. So the motivations were for Hydra 2 is that we had new goals. There was a desire for the unification of viewport and final frame rendering pipelines. As soon as you can put an interactive form of RenderMan in a viewport, it is obvious to think like, well, why are these two different separate things? We should be able to render with RenderMan anywhere where we can use this interactive renderer. So the idea, everyone can render. But the original architecture was neither flexible nor expressive enough. I'll give you an example, like, well, hey, where's the motion blur? And the original GL-based Storm renderer didn't support motion blur, and so the scene delegate didn't have any means of describing motion blur. And we added methods for it, but the manner in which it grew was not as elegant as the original design. And so we kept hitting cases where we needed to add new things that a renderer cared about that were hard to add to the old architecture. The other issue that we hit with trying to squish interactive viewport rendering with final frame rendering is that production rendering pipelines rely on render time proceduralism and have for like 25 years. So when we take those tools away, hey, wait, I'm still using that. And so we needed a way to express those ideas. So I'm going to do a very quick overview of the APIs in Hydra 2. So the primary interface for scene access is called a scene index. And the scene index only has a couple of methods that you implement. And one big difference between Hydra 1 and Hydra 2 is that Hydra 1, the scene was flattened into effectively a dictionary. There was no hierarchy preserved inside of that. And so we wanted to make sure that we could preserve that hierarchy. So this is a lazy interface to a structured scene. And the two primary methods, and there really aren't very many more methods on scene index itself, are get child prim paths. And that allows you to ask, starting from root, like what are the child prims of this? And so this allowed us to unify the notion of like learning what was in the scene rather than having a separate population step. And once you've learned what's in the scene and you want to get information about it, you call getPrim. And getPrim tells you, well, what type of prim is this? And it gives you back its attributes and properties in something called an HD data source. And I'll talk about that in a moment. But note that both of these accessors produce data on demand. So we have preserved this notion of like only read what you need and the laziness of the original Hydra. So what is a data source? A data source is an interface for structured attribute access. So the first data source I'm going to talk about is a container data source. And a container data source kind of replaces the notion of a fixed struct. It is enumerable. And you can access its fields lazily because you can say, hey, get me the names of the data sources that are inside this data source, and then you can ask for the ones that you want, and there's no requirement that any of it be produced up front. And so container data sources are also nestable, so you can have sort of a hierarchy of attributes. But eventually, you need to get to something that has a value. And so we'll talk a little bit about a sampled data source. So a sampled data source allows you to ask it, hey, what time samples do you have that are inside of this shutter interval? And then you can ask for the specific time samples that you want. So I mentioned this relative to the motion blur case before, where it was awkward to introduce new sort of alternate ways of asking for motion blurred values, where we've built these kinds of things directly into the attribute equivalent at the Hydra level. So the next thing I want to talk a little bit about is Hydra has schemas. And this is similar in concept to USD, which has schemas. And the purpose of a schema is to allow you to interpret the data. In USD, it's the data on a prim. And in Hydra, it is the data associated with a specific container data source. So the example I'm going to use would be the Hydra mesh topology schema. Right? In Hydra 1, mesh topology was a structure, right? Like a C structure. It had a fixed number of fields, and when you asked for it, you got all of that information up front. So the idea of a schema is that you give it a container data source on which to interpret, and it presents interfaces that will do the queries and type checking and casting necessary to return the value. So when I instantiate a mesh topology schema on a container data source, and I ask it for face-first indices, it knows to ask the container for a field of a given name and to make sure that it is of the correct type. This is also very interesting because other information can ride along inside of the containers. So if you wanted to describe maybe a renderer-specific addition to what would go into mesh topology, you can put that in there, and you would just subclass the schema to include your additional fields. So I mentioned that attribute data, even on a per prim basis, is hierarchical and structured, so we need a way to address that. So in USD, we refer to prims with an SDF path. And Hydra uses that as the identifier for Hydra prims as well, but we needed a separate path-like identifier for addressing attributes. So in this case, we have a locator, and it really has three path elements: mesh topology, and face vertex indices. And you can see how that aligns with the previous structure that I was showing. Locators are also very important for invalidation, and I'll cover that next. So Hydra 2 has this notion of Hydra scene observation. So any scene index can have registered observers which will receive change notices and information about that scene. So for example, every scene index observer that's listening to it will learn in these vectorized notices, meaning what prims were added. So you get a list of prims and what type each prim is. Same thing with removed. We have a way of expressing when things are renamed, so in case it's more efficient than to add and remove. But the really exciting one is that you get a vectorized set of which prims are dirtied. So for each entry, you get what path to the prim, and you get a set of locators. And I already mentioned that the locators are hierarchical identifiers. That means that the granularity of invalidation in Hydra 2 can be as specific or as wide as you want. I'm going to contrast this with Hydra 1, which used fixed bit fields, which made perfect sense if you want it to be really efficient and you were writing to one known renderer. But that was an area in which we really hit growing pains. So let's take a look at cases that are scene index observers. So an obvious one is the render delegate. The renderer delegate is going to observe the scene, and it's going to update the renderer's representation in response to that. Another one is that we're not stuck with rendering. We can have user interfaces that introspect the Hydra scene, both from a debugging standpoint as a developer and also potentially to enable user-facing workflows. So this is a screenshot of the Hydra scene browser, and as of like 2302, maybe recently we released that. So the USD view shipping in current versions includes the Hydra scene browser and also C++ source code if you want to incorporate something similar in your own. But the third one is the most exciting one, and that is filtering scene indices. So a filtering scene index is a subclass of scene index. So it is a scene index, which means that it is observable. It sends scene update notices to any observer, and anybody can get access to the scene through this. But it also has a scene index observer that can observe other scenes. So in order to fulfill requests, it has the ability to forward or modify either the data or the notices observed from its scene to its own observer. So you can modify the scene in any way, including topology changes, new attributes, anything you want. So you build a pipeline out of these. So let's say we had a scene index that represented a USD stage, and we might do another scene index which substitutes some of that for levels of detail in cards. We might do instance aggregation, and that subgraph can be sort of equivalent to what the USD scene delegate was in the past, but it's modular. So you can append to it, and you can replace pieces with it. So maybe we also have scene indices that are like scene delegates for application or for data that is native to your application that was never in USD. So native Maya objects, native Presto objects. We can use a merging scene index, which is a special filtering scene index which combines multiple inputs. And then maybe we want to do some procedural evaluation downstream of that, some material edits in ways that are more efficient to do downstream. Maybe we want to do X-form flattening. I already mentioned that in Hydra 1, the scene was already flattened down to the leaf. Well, in Hydra 2, that is a choice that you can make. If your renderer wants it flattened, you put a flattening scene index. So the renderer might be observing this portion of the scene. We have a browser that can look at it all the way at the end, but the browser can be targeting any scene within there. So it allows you to choose what is the most useful representation for what we're currently doing. So I mentioned the USD scene delegate, and so we call that the stage scene index. And in Hydra 1, the USD scene delegate supported plug-in prim adapters for types. So for example, if you wanted to have a TET mesh and you wanted to adapt it so it turned into a regular mesh, you could do that. And then the renderer wouldn't even have to know that it was a TET mesh. The problem with this was that you couldn't extend existing prim types or describe behaviors that might be applicable across multiple prims. So in Hydra 2, the stage scene index also supports API schema adapters. And so this allows for a separation of the description of a behavior from its implementation. So an API schema in USD, so let's say I have a mesh prim. So on my mesh, I would use the USD geom mesh delegate to set its topology and points and everything. But I might want to prepend a funky deformer API schema. Let's say I want to describe some sort of custom deformation that could apply to meshes, it could apply to points. And so I'm going to add that there, and that allows me to put a bendiness property. And with an API schema adapter, I can bring that back over into Hydra. So you can see in the Hydra scene browser, in addition to all the normal stuff that would be associated with that mesh, we also have this funky deformer bendiness, which doesn't mean anything to any part of the system as is. But we can extend the pipeline of scene index graphs. So you'll see that there's like a funky deformation resolver scene index just inserted in the appropriate place. That just means that it is activated whenever it sees a mesh or a compatible prim that has funky deformer properties, and it will do the deformation at that point. I also noted that you're not limited to USD input. And anything that comes through the Hydra scene is compatible with this, whereas putting that behavior all the way back into the adapter at the USD level would make it so that you couldn't funky deform a Maya mesh, for example. So another use case that I want to talk about is generative procedurals. So in generative procedurals, this is a higher level API that is backed by a resolving scene index. And so you have prims that describe the arguments and inputs to a subhierarchy generator. And they can depend upon anything in the input scene. And everything downstream of the resolver seems that procedurals outputs as normal prims in the scene that can be inputs to whatever other operations that you might want. So I'm going to very quickly run through just a simple example of this. So the example code we provide for this is a cube per point procedural. So if we look here, we have in USD, we just have a generative procedural prim. And it has, if we look in the Hydra scene browser prior to procedurals being resolved, we can see that there's a prim var describing which mesh it's going to grow its cubes off of. And if we were to view at the point where we are resolving the procedurals, that instead becomes the actual meshes, which are indistinguishable from meshes that might be earlier in the pipeline. And so we'll use the USD view, and we'll change that property at the USD level to point at the other mesh. So just changing that value, and now the points move over, and instead of like 4 of them, we have eight of them. And that mesh is animated, so when we change frames, it automatically updates the positions and can do so in a finely grained manner. But like 8 cubes is not very impressive. We want this to be scalable, so I will load a different asset, maybe the best asset ever made, and we will target that. And now we have like thousands of cubes on Woody's face, and this is much faster to do than the equivalent operation would be in USD scene description because topology is ephemeral here. Okay, so moving past toys, we have our vegetation system is called Moss or Wonder Moss. We have an implementation of that as a Hydra generative procedural. So you can see this rendered with Storm from USD view. In addition to that, here it is running in Presto. And there are 2 interesting things here. One is the same procedural is running in Storm as is running in RenderMan, whereas in the past we had to build different backends for each of those. And the other thing is that there's no USD involved here. We're growing on meshes that are native to Presto. Okay, so another one is that here's a Houdini engine procedural. So it's running a volume simulation and turning it into a mesh. This is very interesting because if I wish I had a picture of this, but I could aim the cube per point procedural at this if I wanted, and it would work. And these systems don't have to know anything about each other. So it's really about defining pipelines via scene index. So the model, again, is we have our input scene with arguments for downstream execution. So if we had crowd deformation, we might implement that as a scene index. And if we had a hair system that grew on posed meshes, these 2 systems don't have to know about each other. They just work because the data is in the same medium. And this is all definable via plugin. So conclusion before I hand off to Dirk. So Hydra 1, applications can use any render delegate, and that was cool. Hydra 2, execution pipelines are portable and interoperable as well via Hydra 2 as an execution medium. It is not an execution system. It is a place for execution to live that does not impose any specific execution heuristics on the underlying system. And now I will hand it over to Dirk to show what his NVIDIA teams are doing with this. Take your laptop.
Hey everybody, so we'll do this rather quickly, but we're very excited about the interest in OpenUSD from everybody in this community. It really makes us feel super happy to see everybody come to these OpenUSD days and to see how much recognition USD is getting at SIGGRAPH this year. So thank you for being interested. We're very excited. We like the idea of Hydra scene indices as a way to be able to add runtime behaviors into like after scene description and be able to use this to be able to prototype ideas. So some of the things we started with, we looked at transforms and we said, oh, we want to deal with geospatial transforms. This is like when you deal with Deutsche Bahn in Germany and they want to have their trains go all the way around. You have to be able to position things around the curvature of the Earth. So how do you evaluate those transformations? So we used API schemas and we used a scene index to be able to evaluate geospatial transforms. And it was really quick for us to be able to prototype this into our system and be able to implement this using scene indices as a way to extend the runtime behavior that we see with Hydra. Another one was with metrics. How do you deal with centimeters, meters? We were able to prove some ideas out really quickly by using scene indices that way as well. Here's another one. From our history in film, we know and love subdivision surfaces, but the reality is CAD and engineering data comes at us as NURBS or BREPs that we turn into NURBS with trim surfaces. So we implemented a scene index to be able to do NURBS tessellation in Hydra with trim curves and be able to get high quality surface representations from there. So then we said, oh, what could we do that's a little more challenging? So we have Miles Macklin at NVIDIA has created a framework called Warp, where we can take Python code and cross-compile it into CUDA or into C++ and compile it for really fast runtime behaviors. So we wanted to be able to say, can we take, this is a cloth sim running on Warp inside of Omniverse. And we were like, oh, that runtime behavior of running a cloth sim, can we do the same thing using a scene index in USD view? And you can. And we were able to do that really quickly, and it was very fun to be able to play with that. Another example is this. This is an ocean sim from Miles, where we're running 1 million CVs. We take some complicated code that in Python compiled to CUDA that runs this procedural ocean simulation, and we can change the parameters on it. Here we have this directly feeding GPU buffers into our RTX ray tracer. But we wanted to say, like, can we take that piece of runtime behavior, and we wanted to see if we could take that and then pull it into USD view, and we can. So this is Warp running inside of USD view on 1 million CVs and being able to play back that ocean sim. That'd be actually to run that ocean sim as well. I think we were also super excited to see the USD BOF that Pixar ran. Thanks to Florian for being the MC and bringing all this stuff forward so that we can see the advances coming from Pixar, but we can also see that Adobe has a cloth sim running as a scene index, and they showed that with their render delegate. We also saw that Autodesk has a Bifrost integration with it through Generative Procedurals, as Steve showed you, hosted by a scene index. I think it gets really interesting when we talk about OpenExec, because Florian talked about some of the ways in which OpenExec is a runtime behavior that is more built into USD in the way that they see it. It has some things that are different. It can't create new geometry. So OpenExec can coexist with scene indices, and they're intended to run together. So I think, like, as we see, USD can describe a scene, but now we're getting into runtime behaviors and execution. And I think it's great as a community if we can get together and talk about how all these things fit together. I don't know that, like, Hydra 2 is not the end-all be-all, but it's a great way to open that conversation and for us to start talking about how execution behaviors fit in. I think I also wanted to say that we're going to open source a repo where we have a bunch of these plugins in nice, easy to compile build code, including the Hydra 2 scene indices, so that people can use it. Now, we probably don't have time, but I think I just want to do this anyway. So I have a little live demo, which is always exciting. So this is the same that same ocean sim running inside of USD view on a laptop. There we go. So we can play it. And so you should be able to see the time scrubber. And you can move time back and forth. You can see those parameters playing on the ocean sim. You can pop up the ocean sim. And this isn't just playing back a simulation. So we can take the water depth and we can make the water be really shallow and change that water depth, or we can change all of the simulation parameters live. Like, this is a runtime plugin running on the A5000 on this GPU within USD view. Now, the key is that since this is running in USD view, the goal isn't necessarily to run it in USD view, but the idea is that these are runtime plugins that can fit into anyone who's using Hydra and using scene and render delegates. So We love the idea of being able to do these kinds of things with anybody using open source software. This software stack is completely open source, and it should fit in with Maya, it should fit in with Solaris and other places. So that was a quick run through of some of the ways that we're using scene indices at NVIDIA, and we appreciate Steve for creating them. And thank you all for coming today. I appreciate it.